recording on. All right, we are recording now. So with that, on this April 15th, Text Day and whatever other events happening, we're delighted to have Professor Arel-Bundock from the University of Montreal here. Vincent and I met, and I don't even quite know where, over related matters a couple of years ago. And he has, during that time, or had already been working on two immensely popular packages called Marginal Effects and Model Summary, which I think we'll encounter this afternoon, and has done much more work on these as well as on others. A lot of his work is really, really fine work that pops up in corners where you think, gosh, I should have thought of that, or somebody else should have done that. One of my favorite examples is that, for example, with now 23,000 R packages, all of which may or may not have data, nobody really surveyed and made accessible what data files there are. And he has just a package on GitHub, and it's R datasets, I believe. If you just Google R datasets, Arel-Bundock, you'll get to it, and then you get a searchable page with all the data files, which is just lovely. Vincent and I share a bit of an affinity over well-engineered and smaller packages. My students here in STAT 447 have encountered one of those. We lean a little bit on tinyplot, and I didn't plan to extend that a bit more in further years. Vincent has built on top of that with tinytable, which is a bit newer, which may come up again today. These things really follow 80-20 rules. You get most of what you need to accomplish tasks with often a smaller subset of all the requirements. And for these tasks, don't always need to pull in a full tail of dependencies and fragilities. So from an engineering and usage point, I really believe quite strongly in that. But I try to keep these opinions a bit away from the class and the course, so we'll not dwell too much about this. But one thing that occurred to me as we were preparing this guest lecture is that it really fits squarely into the narrative of the course, which is about data science programming methods and different programming languages and tools to facilitate working with statistical data. What Vincent has done with some of his packages is just that, putting layers of code on top of other existing code to make the access more unified, comprehensible, accessible, universal, and comparable. And I think he'll talk a little bit about all that. And that aspect, I think, brings us squarely back to STAT 447, data science programming methods. And we're all thrilled to have him here. So with that, I'll end the intro, take over the screen share, and amaze at us. And we said sort of roughly, we'll keep it at an academic hour. So talk of 40, 45 minutes on one or two topics, and we should have room for some questions at the very end. I think Vincent will be on a full screen monitor so we can't see anything, but I will monitor the chat room. So if there are any questions, not the chat room, the chat record for the Zoom, if there are any questions, pipe them there, and we'll try to get them addressed during the course of the lecture. Thanks.
Are you ceding control of your screen now?
Oh yeah, sorry. I thought you could steal it from me, but I have to stop it first. So I think I give up on mine.
All right, perfect. Well, hello everyone. I'm very excited to be here. This is my last week of teaching, actually. We just gave our last classes here in Montreal, and so this is the last hurrah for me of the semester. So I'm glad to be talking to you about these things that I'm really interested in. I'm really excited about, and I hope you will be too. I'm really pleased to be here for two main reasons, I'd say. The first one is that, in case you didn't know this, in my little corner of the R world, Dirk is an absolute superstar. So you are very lucky to have an instructor like him, and it is a great pleasure and an honor for me that he invited me to this thing. It feels very special, so I'm glad to be here. The second reason is that I'm going to talk to you about a book about our package. that go together, and that I've been working on this for a long time, and I'm still excited about it. I still think it's useful. I still think it's powerful, and I'm glad to be able to discuss it with you, to chat, to exchange, hopefully. I see that this is not a, like there are not 200 people in the group, so there's plenty of room for you to interrupt me, to ask questions. So throughout the presentation, you can put stuff in the chat. I'll try to answer, but also just feel free to open your mic and interrupt me. I'll be very happy to answer any questions, to develop more on something you may be curious about. It really doesn't matter what. Just interrupt. I'm really happy to talk. Okay, so are we all good? Can I get a thumbs up if you're ready to start? Give me a signal. All right. I see Jordan is saying go. I will listen to you. Okay, let me do this screen share here. Okay, participants. I think I can get the chat on my screen. All right, let's go. Okay, so the topic of the first part of the presentation is model to meaning, or how to interpret statistical results in R and Python. So just a few words about me. You've seen this on the ad, so maybe there's no need to spend too much time on this, but I am a political scientist who's really interested in statistical computing. So I'm social scientist at the University of Montreal. I am currently an executive editor of the R Journal, which I find an important venue for publishing stuff that we care about. It is a good resource, and it is a good place to get academic credit for contributions that would otherwise go unnoticed. So I think this is a really important endeavor. There's lots of really interesting articles in the R Journal. So if you're looking for something in that space and you want an introduction to some area of statistical computing or to a specific package, I'd strongly advise you to look at the latest issues. Lots of cool stuff. All the articles are free. Go there. I've been developing R and Python packages for quite a while now, including the one that I'll talk about today, marginal effects, and later maybe tiny table if we have time. All right, so this is just a kind of a preview of the tiny table. That's the second part of the presentation. I just want to give you a taste of what's coming. But this is not what we're going to start with. We're going to start with marginal effects, or model to meaning. And the motivating, what really pushed me to go in that direction is a thesis that I have. And I know that some of you are statisticians, so this may feel a bit heretical to you, or maybe not. But my thesis is that fundamentally, a lot of the parameters of our statistical models are basically incomprehensible. So we specify these complex models to maybe capture some part of the data generating process. Maybe we want to satisfy some assumptions to compute an estimate that we really care about. And to do that, we fit models with parameters that are in themselves not very easy to interpret. So I want to provide a path forward, a way for you to maybe add some meaning to those parameters to allow you to compute quantities of interest that are clearer, that are more understandable to your audience, to your colleagues, to your readers, essentially. So the idea is that we should use, that's my argument, right? That the parameters are difficult to understand. So what should we do? Well, we should use our models. We should use the parameters to produce more meaningful quantities. And how do we do that? Well, we take the parameters, we make some predictions with the parameters. And here, when I say predictions, it's not necessarily a prediction about the future. It's not a forecast necessarily. A prediction is just the expected value of the outcome for different parameter combinations, or for different values of the predictors. So we take your parameters, you take your predictors, and you make some predictions with them. And then you make multiple predictions. You combine those predictions to get an estimate of some quantity of interest, some estimate. So that could be the average treatment effect, could be the average treatment effect on the treated, could be, I don't know, a conditional treatment effect, something like that, right? So the idea will always be the same here. You fit a model, you get some parameter estimates, you convert them into predictions, and then you use those predictions, you combine them into some quantity that you actually care about. Some quantity that is meaningful to the world, that is actionable, maybe. And so some quantity that is more interesting than some logit coefficient. All right. So I just want to give you a bit more sense of what I mean when I say that parameters are mostly incomprehensible. So this is a very straightforward example that you see in intro statistics and the social sciences, at least. I'm sure you've seen this in your training as well. So let's say you want to model. So okay, so I'm butchering the notation here. This was written too quickly this morning. Don't worry about it. It should be understandable. So the idea is that I'm making a prediction for the outcome y. So what's the predicted probability that y equals 1 given some predictor with some value, so x equals 1. The challenge here is kind of cognitive. It is about people's reading ability for these probabilities. So we know from a lot of research in psychology and behavioral economics that even a simple quantity like this is actually very hard to understand. So in practice, people will see a probability like this, and whenever the probability is high, they'll just treat it as if it was a sure thing, as if the probability was 1. When the probability is pretty low, they'll just say, this event will never happen. You can think about this. I'm sure you remember some elections in the past where some candidate maybe had a high probability of victory and everyone thought it was a sure thing. Well, turns out it's not always a sure thing, right? Probabilities are more complicated than that. And the problem is that people don't see the nuance in the probabilities. So high probability, people treat it as 1. Low probability, people treat it as 0. When you're in between, people treat it as a coin flip. So this is kind of a cognitive bias that is well understood. It's well documented. Probabilities are difficult for people, difficult to understand. Now look at something like this. This is a odds, right? So you have a probability on top, and then in the denominator you have 1 minus that probability. So if you agree with me that probabilities are difficult on the left-hand side, then you will agree, I hope, that a transformation of probabilities like this is quite complicated, right? It is difficult. So maybe not difficult for gamblers, but difficult for pretty much everyone else. So if odds are difficult, odds ratios are very difficult, right? So this is, I mean, pretty straightforward, but for statisticians maybe, but for the rest of us, for your readers especially, for the researchers you work with, this can be very difficult. And if this is very difficult, then this is basically impossible. And what is this? Well, it's a log odds ratio. It's a logit coefficient. So my point here is pretty straightforward. It's pretty simple that probabilities are difficult. And when you have very complicated transformations of probabilities, they become extremely difficult to interpret. The challenge is that a lot of our statistical models are parameterized in terms of these weird transformations. That are very convenient for mathematical reasons, but that make the interpretation of our models quite difficult. All right, so let me give you a concrete example of this. And this is data that I'm going to come back to over and over throughout the presentation. So this is data from a study by Rebecca Thornton, published in 2000s in a high-profile economic journal. The research question in that paper is actually really important and interesting. So one issue that we've noticed is that in certain areas in Africa, there's really high rates of HIV. We want to fight the propagation of this sickness by testing people, by giving them information about their own status. But the problem is that we go to people, we test them, but people don't then go to the clinic to learn their results. So even if you go to their homes, you take some blood and then you go test that blood, it is not necessarily useful because people will not actually seek out the test results. So they'll do the blood test but then they won't learn the result. So in that paper, what they tried to do, what the author tried to do, is incentivize people to actually go seek out the information. So the design was like this. They did HIV tests at home. That's in a rural area of Malawi. So they did the free HIV tests at home. Then they sent the blood to the clinic, and they offered a reward for people who were willing to go to the clinic to seek out and learn their test result. So this is a really standard randomized control trial. The control group gets no incentive. The treatment group gets something like $2. So they actually varied the amount, but this gives you a sense. So imagine some people get nothing. The other group gets $2 if they go to learn to the clinic to learn their result. And then the outcome is one if the person goes to the clinic. It's pretty simple, right? We just want to incentivize people to learn something. So just to give you the result already, this worked super well. So when you give money to people, they will go to the clinic. They will learn their test results, and the people who test positive actually demand more condoms. So this was in the context of the study, the intervention was treated as a success essentially. Okay, so this is the empirical setup. This is the data that I'm going to look at. Now, to get access to the data, you can do it with the marginal effects package. So that's the package that I want to introduce today. I'm just loading it in R. So I assume that you've all played with R in this class for sure. So I'm loading marginal effects, then I'm calling this get dataset function that just downloads some data from the internet and reads it as a nice data frame. The data frame is called that. So I fit a GLM model with the outcome, which is a binary outcome. Incentive is just 0 if you don't get the money, 1 if you get the money, and that's randomized. And then just for fun, it's not really important, but I'm going to control for 2 variables, the distance to the clinic. The idea here is that if you live really far from the test clinic, you're less likely to go to the clinic to learn your test result. And then a categorical variable, that's 3 categories for your age. So people under 18, 18 to 35, and then above 35. So I'm just controlling for this. Fitting a logit model, and then when I fit the logit model, I get this result here. That's the main coefficient of interest. That's the coefficient that informs me about the association between getting the incentive, getting the $2, and the probability that I go get my result at the clinic. Now, going back to my motivation, that parameters are mostly incomprehensible, I'm asking now, how can we interpret this coefficient, this 2.024? Well, the issue is that this is kind of a complicated function of probabilities. I've already told you that probabilities are difficult to interpret for most of the population. Maybe not for you statisticians, but certainly for your readers or your colleagues. And so interpreting this coefficient is actually not that straightforward. I mean, we have a bunch of tricks. We have heuristics. We can look at the sign. So this is positive. So maybe getting the incentive increases my probability of seeking the result. We can look at the statistical significance. There's kind of a fun rule of 4 if you don't know it. It's kind of cute. Like you can divide the coefficient by the logit coefficient by 4, and it gives you an upper bound on the effect size on the probability scale. But all of these are kind of hacks, right? They're partial information. They're not really actionable. It's not clear what we're doing with that information. And most importantly, this is a super, super simple model, right? It's just a logit that's a model most applied statisticians are familiar with. And it's all the coefficients are entered linearly in the equation. There's really nothing weird about this model. But what do you do when you have interactions, when you have splines, when you have maybe a multinomial model, or when you have some crazy machine learning approach? In all of those cases, the coefficients, the parameters are even less interpretable. They're even harder to make sense of. And so what I want to do here is give you a solution, give you a workflow that is consistent, that allows you to interpret a really, really wide range of statistical models in a way that is principled, in a way that is easy and in a way that will allow you to communicate your results to your audience more clearly. So the solution that I'm proposing is to do post hoc transformations. So you're going to fit a model that is appropriate to your circumstances. You're going to then use this package to transform the parameters of the model into a quantity that makes more sense, that is more intuitive, that is more meaningful, that is easier to interpret. All right. Are there any questions so far? Should I stop, go faster, go go slower? Thumbs up. People are very happy. All right. Great. Thank you. Okay. So what do we do? Post hoc transformations, I'm suggesting that you should ignore the coefficient estimates, basically. I mean, you can still look at them for maybe diagnostic purposes, but mostly ignore them. Transform them into basically three quantities and then do some stuff with it. So the three quantities that I'm going to talk about are going to be predictions, what I call predictions. Those are like fitted values, maybe. Counterfactual predictions. I'm going to explain what that is later. Not in this talk, but in the book, I also talk about slopes, which are really interesting and useful. And then that's going to be the killer application here, the hypothesis and equivalence tests machinery that is built into the package and that allows you to do a lot of really, really cool stuff. So this is all based on standard theory, nothing really fancy here. So it's just the plug-in principle and some nice properties of maximum likelihood estimators. The idea is that you can just estimate your coefficients and then transform them into other quantities. It's really standard. What I'm doing here is not inventing new theory, not proposing a new method. What I'm doing is exactly as your instructor said it in the introduction. I'm building a code infrastructure, a statistical computing infrastructure on top of existing packages in order to make those transformations easier, in order to make them more consistent, in order to make them work across a bunch of models. All right. So what this infrastructure is, well, it's the marginal effects package. It is a one-stop shop for interpreting statistical models and also machine learning models. So I'll mention this later if some of you are interested, but it also works with tidy models and with the ML3, so two big ecosystems of machine learning implementations in R. Uh, I should also mention that I'm focusing on R here, but there's a parallel version of this package in Python that works with most of the big model fitting packages in Python, including stats models, PyFixest, including scikit-learn as well. So basically you install this package, you learn how it works, and then you can interpret the results of basically anything you can fit in R, mostly anything. I've done a lot of, well, okay, I shouldn't say anything. There's still a lot of packages that are not supported, but 100 plus types of models, all of these model classes that everyone knows about. Really, the main ones are covered. It is a simple and unified interface. And in the book that I'm going to talk about later, I also present a conceptual framework that maps kind of the statistical underpinnings to the arguments of the functions in the package. So this is, honestly, I still think it's pretty cool stuff. Like it's very flexible. It's very easy to use once you wrap your head around it, and you can do a bunch of things. So I encourage you to listen to the rest of the talk and then to go to marginaleffects.com to learn about it. So here's just a quick list of a bunch of things that you can do with this. So I've told you almost any model is covered. Well, It works for frequentist and also Bayesian models. If you're doing just a simple logit, an OLS, or some general additive model, or maybe I mean some mixed effects models, I mean multiple multi-level estimation, something like that. It's good for causal inference. It's good for observational data. It can do deal with interactions, conjoint experiments. You can do IPW with this matching. There's a bunch of stuff. So that's the book I keep talking about. Not because I want to make money, because the book is free online. So don't buy it. Just go online, marshallfx.com. I mean, buy it if you want, but marshallfx.com, it's free. Um, go check it out. All right. So here's the Marshall Effects game plan. I want to first introduce you to the machinery to conduct null hypothesis tests. These are standard wald tests. Then I'm going to talk about predictions. Again, here, when I say prediction, it's not a forecast. It's more akin to fitted values. And then I'm going to talk about counterfactual comparisons. These counterfactual comparisons, as you'll see, is just make several predictions and then combine them or compare them to one another. We'll conclude this section with a Q&A, and then if we have time, we'll talk about tiny table. All right. So what's a null hypothesis test? Well, you all know this. It's the answer to this question. Can we reject the null hypothesis that some coefficient, or maybe a function of coefficients, is equal to a value h is 0? So how does this look like in R? Well, you can use the hypotheses function, which is from the marginal effects package. So you start with the model that we fitted earlier. That's the GLM on the HIV randomized control trial. I'm storing the coefficients in this vector called B. And here you see the coefficients, right? The coefficient of interest is the same as before. It's 2.024, right? That's the same estimate I showed you earlier. Now, if my question is, can we reject the null hypothesis that this coefficient, the h cat over 35, is greater than this coefficient there, right? So I'm saying like this one minus this one equals 0. So it's just a null hypothesis that they are equal. And basically the category, the quantity that I want to compute is the difference between these two coefficients. So I can use the square bracket syntax to take one minus the other. The difference between 0.25 and 0.035 is this, as 0.22. Okay, so I've taken the difference between two coefficients and I've asked the question, are these different? Well, if I just look at the coefficient, they seem different, but can I actually reject the idea that they are different using some p-value or from some hypothesis test? And I can answer this question by using the hypotheses function. So if you've used maybe the CAR package, there's a linear hypothesis function in there. So this is basically a souped up version. It's a more powerful version of that. Okay, so what I do is I do hypotheses, I do mod, that's the model that I fitted, and then I specify my null hypothesis using a string formula. So here B5 is the fifth coefficient. So 1, 2, 3, 4, 5. So the fifth coefficient minus the fourth coefficient is what I'm doing here. The difference between these two is 0.218. And then once I specify all this and I run the hypotheses function, I get all the niceties that you can see here. I get the standard error, I get the p-value, and some nice confidence intervals. So what I can say now is that the difference between these two coefficients is probably not 0. I can reject the null hypothesis that these two coefficients are equal. You can see that the p-value here is pretty small. Okay, so this is a very simple comparison between two coefficients. It's a very simple null hypothesis test. You can do a lot of things, right? So this string specification it's kind of weird to specify a comparison as a string like that, a formula as a string. It's not standard R syntax, but it allows us to be extremely flexible in the specification. So I can do the first coefficient minus 10 times the log of the second coefficient and specify that as a null hypothesis. Or I can say I want the difference between these two minus the difference between these two, which could be like a difference in differences. Or I can do anything, right? This is extremely flexible. So these two null hypotheses here are silly. They're not really interesting, but they're here just to show you that the infrastructure is very powerful. So if you have a very specific argument to test about the relation of two coefficients or about the relation between two predictions, you're going to be able to do what you need with this. Okay, so this is flexible. All right, so I'm showing you this simple hypotheses function, and I'm applying it to coefficients, even though I told you that coefficients are not particularly interpretable in many models, even though I told you that the parameters are not super meaningful. I'm doing this not because I care necessarily about the coefficients themselves in this model, but I'm doing this because the same mechanism, the same machinery that I've just shown you works as well for coefficients as it does for any of the other quantities that are computed by the model, by the package, sorry. So this is really the killer application, the killer feature of this package for me. So when you do predictions, fitted values, or if you do counterfactual comparisons, so like a risk difference or an average treatment effect or a conditional average treatment effect, well, what you're going to be able to do after that is conduct very complex, if you want, hypothesis test between these different quantities. So you're going to be able to say the average treatment effect in the group of treated individuals is 2. The average treatment effect in the group of untreated individuals is 4. And then you're going to be able to run a hypothesis test to know, is the treatment effect stronger in one group than in the other? So you're going to be able to compare formally the strength of a treatment effect, or you're going to be able to compare formally the predicted value of the outcome in two different groups. So this is going to be a very flexible, very powerful, very important for many research questions. Okay, so this is the kind of the generality pitch. This is why hypothesis tests are really important here. Now, let's move on from coefficients, from simple hypothesis tests to one of the main quantities of interest here. So if we're not focusing on coefficients, what do we care about? Well, predictions is one of the main things. And here, again, I'm not saying it's a forecast. I'm just saying a prediction is the outcome that my model predicts on a specified scale. So it could be the response scale or the link scale. So it is the predicted outcome by my model for a given combination of predictor values. So in the context of the example that I'm in our running example, right, it could be the predicted probability that an individual will go to the clinic to learn their HIV test result, right? And that given individual would have certain characteristics. Maybe they live 1 kilometer from the clinic. Maybe they are underage. Maybe they're under 18, right? So it is the outcome predicted by the model for a specific individual, for a specific unit with some characteristics. Okay, so this is really akin to fitted values. In the package, there are going to be three main functions to deal with predictions. First one is, well, predictions, and then average predictions, and then plot predictions. I imagine that you can guess what these functions do. Okay, pretty straightforward. Okay, so this is really mostly for my students who don't do a ton of stats. Maybe I can skip this, but this is just a reminder that in the logit model, you can get predictions basically as a two-step process, right? So this is the intercept, this is the first coefficient and the first predictor. This is the second coefficient and second predictor. So I can get predictions on the link scale by plugging in the coefficient estimates for B1, B2, B3, and then by plugging in specific values of X and Z, right? Then when I have the predictions on the link scale, what I can do is just transform those predictions using here the logistic function. And that gives me a prediction on the response scale. Okay, so this is just going from coefficients and predictor values to a predicted outcome. Okay, Concretely, what does this look like? Well, this is just an equation for the model that I estimated earlier. There's an intercept, there's the incentive dummy, right? Does someone belong to the treatment group where they receive $2 or to the control group where they receive nothing? The distance of uh, the distance between the person's home and the clinic where they need to go to learn their test result, and then the two age categories. This is kind of terrible notation, but you see what this is. Like this is people over 35. This is 18 to 35, and so on. So what we can do is just plug in the values. So let's say I'm interested in the predicted outcome for one individual who did get the incentive, lives 2 kilometers away from the test center, and is over 35. So this person got the incentive. There's a one here instead of a zero. They live 2 kilometers away from the test center. They don't belong to the 18-35 categories. They do belong to the over 35 category. Okay, so I'm just plugging in the values for this particular individual. I'm plugging in the coefficient estimates that I got from the estimation, right? Remember, I use coef to save the coefficient estimates from my model into this vector. And then I use the the logistic function to convert these to the response scale. So this is just a code translation of the equation above. So what I get from this is I get an estimate of the predicted outcome. So this is interpreted pretty straightforwardly. It says that my model predicts that an individual who did get the incentive, a person who gets $2 to go to the clinic, and who lives 2 kilometers away from the test center, has about an 82% chance of actually going to the clinic and actually learning their test result. So remember, everyone gets the test, but only some people go to the clinic to learn. We predict that this specific individual will have about 82% chance of going, or an individual with these characteristics. All right. So this is the way to compute it by hand. It is annoying. It is error prone. It's not a good process. I don't recommend you do that. Instead, what you should do is use this predictions function. So what's interesting to note is that the predictions function is actually designed to be really closely parallel to the predict function. That's a method that is implemented by most statistical packages in R. And it is a method that I actually use under the hood to do this. So predictions is sugar around the built-in R predict functions. So what this means is that it behaves pretty similarly, and also that the arguments are very similar. So in the predict function in R, you first feed it the model object, and then you use the new data argument in order to specify the characteristics of the individuals or the units that you care about. So here I care about someone who got the incentive, is over 35, and lives 2 kilometers away from the center. And so what I'm saying is the new data is going to be that person. And then I'm going to use a data grid function, which is a helper function from the marginal effects package, in order to be able to specify these things more easily, right? In the previous one, I had to say to remember that the kilometers is relevant to the third coefficient, and I had to place it there in the formula. The incentive the same way. Here, I don't have to remember any of this. I just have to say incentive 1, distance 2, and here's the age category. And by doing this, I get an estimate of the probability of getting the outcome. That's 82%, right? But the nice thing is you get the confidence intervals, the z-value, etc. All right, you can do this with many values of the predictors. So you can have vectors, or you can even have functions that return vectors. So let's look at this code. I'm doing predictions mod for new data, that is for the description of the individuals that I care about. And that description is going to be this. So first of all, I'm going to look at two different age categories, this one and that one. Those are age categories in my original data set that I might be interested in. And then for the incentive, I actually use a R function here. So I'm not even saying explicitly what the values are, but what I'm doing is I'm saying to data grid, take the unique function, go back to the original data that we used to fit this model, and take out all the unique values of this function, of this column here, of this variable incentive. So what I get is two values of each categories, and then incentive is a binary variable, so I get also two values, right? 0 and 1. 2 times 2 means I get four combinations of the predictors. So you can see here that each row represents one combination of predictor. In the first row, I see that for a person between the ages of 18 to 35 who receives no incentive, that's a person in the control group, well, that person has about a 32% chance of getting their result at the clinic. For a person in the control group in the same age bracket, you get about a 78% chance of getting the result. And so think about it for a second here. What have we learned in this? Just look at the two rows and try to think about what we learned. Well, it seems pretty clear to me that the incentive works, right? In one group or for one type of individual, the probability of getting the result is super high. For the other one, it's not so high. Okay, so I already have an inkling that the incentive might have worked, and we're going to later show this more rigorously. Okay, so now I've shown you predictions for single individuals. Just for your information, when you don't specify new data, when you just say predictions for the model, what marginal effects is going to do is it's going to retrieve the original data from your that you use to fit the model, and then it's going to make predictions for every single row of the data set. So this has 2,800 something predictions, always on the response scale. So this can be kind of useful. Okay, now just one thing that is super useful is what you can do is make all these predictions, the 2,800 predictions. You get this. It's okay, the numbers don't match there, but this is because of listwise deletion. So you take the mean, the average prediction, but you can get which is 69%. Well, you can get the average prediction with this. Average predictions, what it's going to do under the hood is retrieve the original data set, make predictions for every single row, and then report the average prediction there. Okay, super important, super useful, average predictions by group. So what you can do is, again, make predictions for every single row in your data set and then average them by subset. So here I'm saying make the average predictions by subgroup. So I have the average predicted probability of getting your test result from the clinic in the below 18 people is 67%. The average predicted probability of going to the clinic and seeking out your test result is about 72% in the above 35 group. So here what you see is pretty interesting, I think. So you see that the older people in general have a higher predicted probability on average of getting their test result than the young people. So there's clearly a difference here numerically, at least, between these two estimates. Well, there is a numerical difference, but I want to know if this is statistically significant. I want to know if this difference between the 72% and the 67% might be due to sampling uncertainty. So what I can do is use the exact same syntax as before, this kind of formula here. But instead of applying it to coefficients, I apply it to average predictions. So this is what I was telling you earlier. The hypothesis functionality, this machinery, is available in every single one of the marginal effects package functions. So you just use the exact same thing as before, and then you add this hypothesis argument. And what this allows you is to compare different average predictions, different estimates. So I'm going to do 72% minus 68%, 67%. That gives you about 5 percentage points difference. This 5 percentage point difference has a standard error of this, and the p-value is just above a standard threshold of 5%. So in this context, if I had adopted this threshold, I would conclude that I cannot reject the null hypothesis that these two estimates are the same, right? I cannot reject the null hypothesis that on average, people under 18 have the same probability of seeking out their test results than people above 35. So although these two numbers, this one and that one, look different numerically, statistically speaking, I cannot reject the null that they might be the same. Okay, so this is this is really important for me that you can have all of these estimates created by the functions and marginal effects, and you can then compare them more robustly. So very quickly, you can have robust standard errors clustered, you can have bootstrap, you can have a bunch of things. There's functionality to plot these predictions to make nice plots. That's easy, and also a very important thing is that you can apply exactly the same workflow to any model you fit, any of the hundreds of models that are supported by marginal effects. So the first model that I've shown you, it was the one where every coefficient was just entered additively, right? Incentive plus age cat plus distance. Well, I can do interactions, or I could include splines in my model, or I can fit a completely different model, doesn't matter. The predictions function, the average predictions function, all work exactly in the same way as before. So it's many models, but just one workflow. Okay, so I want to very quickly, we don't have that much time left, so I want to go very quickly on this idea of counterfactual comparisons. What I mean by a counterfactual comparison is pretty simple. So you make one prediction for someone in the treatment group, one prediction for someone in the control group, and then you compare those predictions. They're counterfactual because we don't necessarily observe both, right? For a single individual, we observe only the outcome for the treatment that they actually received. That's the fundamental problem of causal inference. But here we're using the model to essentially impute the outcome that is expected under different treatment regimes. So we're making a prediction in the control group, making a prediction in the treatment group. So this is just the same idea. So here's the prediction of the outcome in the treatment group. Here's the prediction of the outcome in the control group. Once we have those two quantities, we can compute many quantities of interest. So we could do a difference, right? You could do a ratio. You could do an average difference, which would be an average treatment effect. Um, Okay, so we can skip this. Just showing you how this works in the code. So imagine that I'm interested in switching from 0 to 1 on the incentive variable. So I'm interested in the effect of getting that money on the outcome, which is, do I go get the result at the clinic for a specific individual who's 35 and over and lives 2 kilometers from the test center. So what I can do is I use the comparisons function. I specify that the treatment variable, the variable that I'm interested in, the shift that I care about, I specify that with the variables argument. I'm interested in the incentive. And then I do the same thing I did with the predictions function before. I just specify for what kind of individual I'm interested in. And here what I see is that the comparisons function says that the difference between the predicted outcome in the control group and the treatment group is about 44 percentage points. So just giving $2 to one person, to a person that looks like this, right? A 35-year-old individual living 2 kilometers from the test center, increases by about 44 percentage points the probability that they will go to the test center to get the result. So this is a massive effect. All right. So we can do the same thing as before. If we don't specify new data, we get the estimate for every single row of our data set. And using the average comparisons function, like this, with my model and with the variables incentive, I get very easily an average treatment effect. Okay, that's the ATE. The ATE is about 45 percentage points. So under the hood, when I do average comparisons like this, I get the ATE. I get something that some of you might have heard people talking about. That's G computation, essentially. You can do a conditional average treatment effect by using the by argument, which is again the same thing as we did with predictions. You can also do the ATT and the ATU by doing the by argument. You can do the effect of a change of 5 units of one standard deviation of moving from the minimum to the maximum. The function deals very well with categorical predictors as well. So all of this is trivial. All of this is supported. Risk ratios. Um, One last thing that I want to show you is this. You can do average comparisons by age category. So that gives you three average treatment effect estimates or conditional average treatment effects estimate. So in the group of 18-year-old or under, the effect of getting the incentive is an increase of about 48 percentage points in the probability of getting the outcome. The counterfactual comparison or the conditional average treatment effect in the group of people who are 35 and older is about 44 percentage points. Similarly to in the prediction case, we had different numerical estimates here. And I can, as before, use the hypothesis argument to compare these two. All right. So my question here is the effect of the incentive stronger for older people than for younger participants? Or is the effect equal in the two groups? And here the p-value is large, which means that I cannot reject the null hypothesis that these two groups are the same. All right. Um, Again, plots, very nice. And what I want to emphasize lastly is that all of what I've shown here is very consistent in terms of arguments and the R functions, but it works for basically any model that you may have. So it's the same syntax. It's a compatibility layer over a lot of models that are really different in R. So that is my pitch for marginal effects. Now, we don't have that much time, but I hope that this was interesting. And if you have some questions, I can stick around. I'm happy to answer and to chat with you.
Yeah, happy to open the floor. So if you have questions, just
Yeah.
unmute and jump on in if there are any. I think everybody wants to see Tiny Table.
All right, let's do it. Um, how much time do I have? There.
I'm cool. I mean, that's the advantage of doing this from 4 to 5. There shouldn't be any lectures after it. So maybe,
All right, so let's just run through those slides and I'll try to do like a 5 minute thing. It's just to give people a taste of what they can do with that. All right, so Tiny Table is a side project that I got pretty excited about. Turned out to be way more work than I hoped. But anyway, okay, so Tiny Table is small but powerful. So I just want to stick around on this slide for a little bit, just to show you a few of the things that this package can do. So all of these tables were created with the same package that is completely dependency free. So it does not import any R package except base R. And yet, look at all that you can do with this. So this is a LaTeX table with groups, colors, group headers. So there's spanning column labels. You can have footnotes. You can have different colors, different text size. These at the end are kind of crazy. I got inspired. I copied tables that had been done elsewhere in Tiny Table, but I hope that it can show you how flexible this is. The syntax is very simple. It is concise. It is pretty safe. So if you input something that is wrong or unexpected, Tiny Table will fail very early and tell you what you should do instead. Overall, I think it's kind of nice to use. So if you ever need to draw tables in HTML, LaTeX, types, or Markdown, or even Word documents via Pandoc, then that might be useful for you. Okay, so some design pillars. So one thing that I really wanted to do with this is to have a simple package that was simple to use, but also produced simple content in terms of the files that they generate. So when you look at the files that Tiny Table generates, you're always going to be able to see the data there. There's a data, and then there's a style sheet that comes on the side, which makes it easy for you to modify, to edit, to do whatever you want with it. So these are the design pillars. Um, these are the output options. So I've already mentioned them, but you can do HTML, Word, Markdown, types. I don't know if you've looked at types. It's kind of an interesting project. So they pitch it as an alternative to LaTeX. Um, it's kind of great. It compiles very quickly, so you can get almost live preview when you edit a types document, which is a neat feature. So check it out if this sounds interesting. But Tiny does all this using save TT. So how this works is in this case, X is a data frame in R. TT is tiny table, and this creates a table. And then I'm piping this table into save T and just saving it to file. If I'm not piping it, usually you'll just have a nice printout. If you're in a IDE like VS Code or Positron or RStudio, you'll get the nice window pop up on the side with your table in it. Um, Print just decides what format you want. If you don't specify the print, you'll get an inference about the best format for your current environment. So we try to guess what works best for you. Okay, so let's say you want to add style. So you have a table, you want maybe some emphasis, some colors, some backgrounds. We're going to do this in HTML and LaTeX, but also types. In LaTeX, we use the tabular array package, which is really neat. If you are a LaTeX person and haven't looked at tabular array, it is very cool. And in HTML, we're going to do Bootstrap. You can do text colors, backgrounds, widths, heights, everything. So this is just a simple example here. Maybe I should like, zoom out. Here's the key. So let's say I'm creating first a data frame with this. Empty cars is a built-in data set in R. So you open an R session and it always has empty cars available. So here I'm just taking the first 10 rows of empty cars and 3 columns. I'm feeding that to the TT function. So this creates a tiny table. And then I'm piping the tiny table to the style tiny table function. Now, I tried to be a bit exotic here, so I did which is a selector for rows. So I'm saying I, which is the rows, J is going to be columns. So I'm saying for the rows that match this. So in my data set, when AM equals VS, I'm going to style those rows. The background of these rows are going to be teal, and then the color of the text is going to be white. And you can see that the table matches that. So whenever AM equals VS, you get a teal row with white text. And this is automatic styling. It gives you the indexing there. There's many ways to index this. This is kind of a fancy, funny one, but you can do a lot of different indexing styles. You can do things like this. So here in this case, what I did is I did style with the background argument, the same one here to do teal or the color. And then I also did font size with this. So you get here in the top corner, you have a very tiny font, and here a very big one. You can change the background colors and the text. Notice that there's yellow text, and then as soon as yellow becomes too close to the background, then we switch to black. So this is a fancy table you can do. You can format the content as well. So style is one thing, but you also might want to format numbers, dates, strings, replace missing values. Maybe you don't want NAs in your table. So the format TT function is there for you. So imagine I'm creating this data set, this data frame here with lots of decimal points and this one there. I'm saying create a tiny table and then format the content of that with 2 digits. And I want those to be significant digits at the cell level. All right, so this is kind of a nuance in formatting. So we could do the significant digit for all the column or for just on a cell basis, but you can customize all of that. This is another example where we use an external package to format some content. So the scales package has many formatters. So it has a label date, label currency, label ordinal, bytes, percent. So you can use all of this, feed them to the format TT function with the FN argument, and then you get a table with dates, with prices, with ranks, with memory. Okay. So you can have all this. So just showing you that you can format your content. You don't have to convert everything to string before you feed it to Tiny Table. In fact, I would discourage you to do that because it prevents you from doing nice indexing, but you can format everything with the helpers there. You can do groups. Groups, there are two kinds of groups. The first one is a row group. So in this case, I'm saying I like fake hamburgers. This is a column spanning group. So I'm saying here, I'm going to insert in a row. I is always for row indices. I'm going to specify this as a list. I'm going to say the name of the list item is I like fake hamburgers. That's the content of the row. And I'm going to put this in the third position. So this is 0, 1, 2, 3 position. So this is a way to insert groups, row groups. You can also insert column groups that show up as spanning column headers. So let's say these first three columns are hamburgers, then you have the halloumi and you have the tofu. What I'm saying with the J, which is the index for columns, I'm saying hamburgers should span columns 1 to 3. Halloumi should span columns 4 to 5. And then tofu should be only in column 7. So this is pretty standard when you report statistical results, right? You're going to have many regression models, maybe two of them are Poisson, two of them are negative binomial or whatever. So you can have these spanning column headers like this. You can add pictures, you can add plots, you can have spark lines, inline scatter plots. There's so much you can do. So on the website, on the Tiny Table website, there's like way too much documentation actually, but there's about 90 pages of cool things that you can do with Tiny Table. Almost any question you may have is there. So Tiny Table website, marginaleffects.com. There's lots of documentation. I encourage you to look at it. If you have any questions, write me an email or open an issue on GitHub. I'm always happy to chat, always happy to exchange. And if you have feature requests, I'm actively working on these things. So if you have good ideas, I would love to steal your ideas and make life a little bit better for the other users. So don't hesitate. Send me an email, open an issue on GitHub. I'd love to chat.
Fabulous. Thank you so much. That was really awesome. I mean, whenever I look at marginal effects, I kind of go start with the beginning examples, which are very gentle. Yeah, logistic regression. I know how to do that. And as soon as I spend a few minutes, I go, jeepers, creepers. I would not know how to do this by hand. And when you then have to switch to a different model, I mean, this is really, really powerful and versatile. Yeah.
Yeah, I mean, yeah, and that's exactly the thing, right? Like, so you can, like, most statisticians can do that kind of stuff pretty easily if you're dealing with one model, but as soon as you want to try just one variation on the model, or you want to run some robustness checks and to see if your results change for some variation, it becomes a nightmare, right? And you're also so it becomes a nightmare to implement, but it also becomes a nightmare to maintain and to read. Like you want your code to be replicable, you want it to be readable, and if it's just a series of average predictions call where the only thing that changes is a model, then you have a kind of a mental view of what that does, and you can read it much more easily. So I think it's useful to you, it's useful to your readers, and to the people who may want to replicate you in 10 years. All right. Oh, all right. Thank you so much. I'm glad you liked it. Good.
It's been very quiet. It's been a quiet term, but yes. So if there's, no further questions, you already did very generously. offer your coordinates and invited anybody with questions to contact you. And yeah, that's the way to close it out. That's perfect. So once again, thank you so much. That was really enlightening, all that I hoped it would be. And exactly, we can close on some newer practical stuff towards the end with Tiny Table, which is also fun. Not yet. Instead, 447, I don't think we do tables much when we do Markdown. We do plotting a little, so to be seen. But there's always exercises left for the readers or students. So yeah. Once again, thanks for swinging by. This was really lovely. Appreciate it. And I'll keep you posted how it goes with the video when I get it back from Zoom and where it goes. Okay.
Sounds great. Thank you.
Thanks so much. Bye, everybody.